Hey, welcome back. In this lecture, we're going to be discussing the implementations of the three algorithms we've spent the last couple of lectures looking at. The reason I've saved them for all three for one lecture is, as I've said before, the implementations of these two are very close. Plus, it was nice just to sort of learn the basics of the algorithms all at once and sort of just deal with the algorithms on an abstract level. Now we'll dive into the data structures for a lecture. So, first we're going to start with Dijkstra's. And to do that, let's go back to the graph we were using for the Dijkstra's discussion. Now, we had set up this table that we were using to kind of record things on paper. And one approach we can take to the implementation of Dijkstra's algorithm is to use that same approach when dealing with the graph, the implementation itself, where we said we're holding here the table that's indexed by vertex. And then for each vertex, you've got a distance and a marking of whether the vertex is known or not. Now, we're going to assume for the purposes of all these discussions that you can go from, if you're going to keep a table like this, that you can go from the vertex itself to its entry in the table and back and forth in constant time. And either you have some key stored inside the vertex that would be able to tell you, well, look in this particular table, and then in the table you might also have a pointer back to the vertex. Or, as we discussed with the graph implementation, when we started talking about all the vertex nodes and edge nodes we have, and they're hidden, by vertex and edge iterators. Those vertex nodes and edge nodes, the implementations where you ultimately had a list of vertices and a list of edges, and they were all connected the way we described, they also could hold lots of data. We just didn't draw that in the picture because we only had room to draw the pointers. But you can also have plenty of data for a vertex node or for an edge node. And one of the various data you could have for a vertex node would be things like this. A couple of integer fields to store some useful information, or some sort of a mark field so that as you traverse around the graph, you'll be able to mark vertices visited or not, or known or not. And we'll see when we discuss traversals next time that that's of a lot of helpful use in a graph implementation. And so if we had that situation, then we could have stored these values directly in the node. There wouldn't really be a matter of a table necessarily, but those values could have been stored directly in the vertices. And then you could have just said, well, to traverse down the table, in a sense, you would traverse down the list of vertices, or your table or some data structure could simply be pointers to your vertex nodes, which would not only be the vertices, but would have these values as well. You still might want to store within the vertex the entry in the table and make it easier to move back and forth between the vertices themselves and how they're organized. But at any rate, there are ways of making that work. And we're not going to dive into the various different ways of making it work. We're just going to assume we've got it set up somehow so that it works. That if we're on a vertex, we have the ability to jump straight to its table entry, and from a table entry we can jump back to the vertex to say, look at its neighbors. Because that's how we'll need to start out. We'll need to say, well, A is the source vertex, and that'll be what we pick the first time through when we want to pick our vertex to process. We'll need to jump back to A and say, well, now what are the neighbors of A? And the neighbors of A were D and B, and so we needed to be able to jump into each of those cells in the table and say, well, D changes from infinity to 0 plus 5, and B changes from infinity to 0 plus 3. And we kind of had to do things that way. So assume for the sake of the discussion that we're able to transition between the graph and the table with relative ease, and the different ways in which that could be set up could be discussed. But certainly, by throwing a few extra pointers in, you can see that would work. And therefore, we're not going to kind of spend any more time delving into the different ways that might happen. We're going to focus instead on exactly how the table could be used and what the running time would be of keeping track of things. So that said, imagine we have this table set up, and remember the goal of Dijkstra's was to say at each pass of the algorithm, what we're going to do is we're going to say search the table for the lowest, or for the vertex that is unknown or unexplored, and out of all those vertices, the one with the lowest distance. So we're saying out of all the ones that have 0 in this column, we want the one with the minimum distance so far. And so what that will require is a traversing down this table. We need to basically traverse down the table and maybe hold a pointer to some vertex that's the lowest so far. And of course, in this case, now we say, well, there's a vertex with k, our known field 0 and the distance is 0. And as you look at other vertices one by one, then that isn't going to be improved upon by anything. Where later on in the algorithm, we might say, well, here's a vertex with known field 0 and the distance is whatever that distance is. But later on down here, we'll find some other vertex with a known field 0 and a distance that's smaller than the one we had up here. And so through each pass of the algorithm, we'll always traverse down the table and ultimately find, out of the entries that had 0 in this column, ultimately find a distance that is the minimum out of all of those. And as we've, to find the minimum of anything, you're going to need to look over the whole set. So if we're going to keep score here, we can say that using the table, if we're going to actually use an array of some kind to store this table, we can say that traversing to find the minimum distance vertex at each step is going to be order v time. Because we've got this table, we need to search down the table in order to find such a vertex. And so searching down that table will take order v time. And then in step 2, we say, okay, now that we've marked one of these vertices known, specifically, we would have said, well, now that I will have said, now I've marked A known, and I said I explored from A and said, B goes from infinity to 3, and D goes from infinity to 5. And so we'd be holding a 3 on this portion and a 5 on this portion. And we went through that all a few lectures back. But the idea would be now that would be the end of one step, and now in the next step we would say, now, once again, search through the table, find the vertex that has minimum dv among the vertices that are still unknown, still have 0 in the k column. But each time through, we now don't have any information about what we've seen already. Each time through, we'll have to search anew for the new minimum because any of these distances could have been changed the last time around. So now some of you may be thinking, well, I know of a better way to make that run faster, and indeed there is, and we'll talk about that in a moment. But first we're going to try and approach it this way, because there'll be times when this is the way to go and times when a different way is the way to go. So if we're traversing to find the minimum at each step, that's going to be an order v traversal for the table, and then that means overall that will be order v squared. By overall, I mean what will be the expense if we add up all the times that operation is needed throughout the course of the algorithm. And as we go through the algorithm, step by step, well, we're searching for a new vertex on each step. So we will have searched the table and picked vertex A. And then we will have searched the table and picked vertex B. And then searched the table and picked vertex D. And then, if I remember correctly, it was C and G, I think, were tied. Were tied after that, and so we picked one of those two. Anyway, we had to do this pass and picking one vertex each time. Total, we did 7 different passes. And if each pass takes order v time, and we do v passes total, then the total time we spend traversing and searching this table is going to be v squared. And so overall, we spend time searching this table, v squared time. Of course, that's not the only part we need to worry about. Certainly, searching this table each time is going to be something we worry about. But we can say there's also the issue of saying I need to update things. So when I reach a vertex, I say, for example, the first time I say, okay, A is the vertex in the process, and at some point there we have some adjacency list implementation, whether it's something simple or something like ours, where I have here, this is my A entry in a table or a list of some kind, and I'm saying, well, the neighbors I have are B and D, and so at this point we'd be saying, well, when we say for all neighbors of A, do the following, we'd be saying, well, look at vertex B, and then now that we're at vertex B, we have some transition between the vertex and the table, and we say, well, now that we're at vertex B, the distance had been infinity, we said, well, the distance at A was 0, and the edge between them was 3, and so 0 plus 3 is 3, and that's better than infinity, so update that. There's this processing being done here where we say, now that we've selected vertex A, we've done an order V, searched the table, we picked vertex A the first time. Now we're looking at its neighbors one by one and checking for updates. So I look at B, and I say, okay, well, I have to do this idea of looking at the vertex, adding the A distance and the edge between A and B to get a new distance, comparing that to the distance currently stored at B, and if the new distance is better, then do an update. And then I move along and I say, well, now what about D? Look at the distance currently at D, which was infinity. Consider the distance to A plus the edge from A to D, which is the two of them together were 0 plus 5. Is that better than what's stored at D? And if so, then update. Now we're assuming that all takes constant time for each vertex. We said, okay, I'm assuming that I can grab the A entry in the table in constant time, so I know what the DV is. So I can get the DV in constant time. As I traverse these vertices in the adjacency list, I'm assuming I can, from this vertex, grab its entry in the table so I can get the DW, and we'll assume that we have some access to the edge so I can quickly get the cost of this as well. And of course, in our implementation, we have that because when we were traversing along this adjacency list, what we had here was we had the edge. We were looking at all the departing edges of A. And so I said, well, I've got the edge. This was the A to B edge, and then we moved along in that doubly circularly linked list to the A to D edge. And from each of those two edges, we could have followed the target pointer and gotten the vertex B and the vertex D. And so our graph implementation would indeed provide those things because we weren't looking at the vertices here. These nodes represented the edges. We would have had vertex B and D later on in this structure, and then this was represented the A to B edge and the A to D edge. And so we could actually store the edge weights right there, and then we could say, well, from this vertex, it stores its distance. Each of these, you can follow the target pointer to get to that vertex, to B or to vertex D and read its distance, and then the edge node itself would store the cost from A to B or from A to D. So our implementation did indeed provide that, and in general, the adjacency list could store here the cost of the edge, and then you could always have a pointer to your vertex slot, which would hold the cost, the distance of the vertex. So you should have access to those things in constant time, provided you're now at this edge node. So if I'm at edge B, I can always follow, I can have kept track of this or had a pointer back to A, and I can have a pointer to the target, and therefore I can get those, and the edge itself can keep track of that cost. So retrieving those three from an adjacency list implementation shouldn't be a problem. And a good adjacency list implementation, if we're trying to run something like Dijkstra's quickly on it, should provide us constant access to those three values and the ability to update the DW as needed. Otherwise, this will all take longer. But our assumption here is we've got the adjacency list coded with enough information so that I can actually obtain these three values quickly. And therefore, that comparison we had worried about, where we said we compared DW and DV plus the cost from V to W, those two we were comparing, and if we can retrieve those three values in constant time, then we can do that addition in constant time and compare the two in constant time, and if necessary, overwrite the old value of DW in constant time as we did here. So assuming our implementation is such that we've got enough information connections to be able to retrieve those in constant time, and for the implementation we discussed, we do. Then the edge update time would be constant. So I'll say it takes me order V time to find a vertex. Given that vertex, as I look at its neighbors one by one, updating the neighbor cost, this is saying for a neighbor, use the edge to it, use the edge from your current vertex to that neighbor to consider an update of distance. that was what we're dealing with here. We're saying this was the process where we said we're now at some neighbor. We're at the neighbor B of the vertex A, or alternatively, we're at the neighbor D of the vertex A. And we're saying for that neighbor, use the edge to that neighbor, the edge from A to B or the edge from A to D, to consider updating the distance. That's the part we're concerned with here. And that whole process takes constant time. But of course, we have a number of neighbors, and so overall for this vertex, it took me constant time to consider the A to B edge and an update between them, and it took me constant time to consider the A to D edge and an update it might, I shouldn't say update between them, but the update that might cause. The update this new edge might cause. And so the question is, well, how do we add this up? How do we add? Well, we could have had no neighbors of A. We could have had 2 neighbors of A like we had here. We could have had more neighbors. How do we record that cost? And the issue is, well, let's just consider the cost of one particular edge, and then we say at some point every edge will have been looked at. So in other words, let's not worry about saying, how long does this take overall for one vertex? Because that'll vary. Each vertex could have, perhaps no neighbors or many neighbors. So let's not worry about the time for one pass through the loop, the time for one vertex. Let's simply say, for one neighbor of a vertex, it takes constant time. And how many times would that come up over the life of the algorithm? Well, over the life of the algorithm, every single edge will be considered exactly once, because every edge departs something. So when I'm considering the first vertex, I'll look at all of its neighbors, which means the edges that depart from A. Now B will be picked on my next step, and I'll consider all the edges that depart from B. And then D would have been picked on the third pass of the loop through the table, and I would consider all the edges that depart from D. And so on and so forth. As each step through our loop, we traverse the table and find the next vertex to worry about and explore its neighbors. Well, if I explore the neighbors of my first vertex, and then the neighbors of my second vertex, and then the neighbors of my third vertex, and then the fourth vertex I pick, and then the fifth vertex, and sixth, and the seventh. What I will have done over the lifetime of the algorithm is explored every edge, because every edge goes from some vertex to another vertex. So I would have gotten these two when I look at the neighbors of A, and I will have gotten these when I look at the neighbor of B, and I will have gotten those when I look at the neighbors of D, and then I will have gotten, when I'm dealing with these, which would be, what was we had here? 3, and we would have had, this would have been next, I believe. The F and G would have been the next ones we considered. Yes. And so the F and G were the ones we would consider next, and so I would have eventually looked at the neighbors of G, and then F I would have looked at the neighbors of, and there are none, and then I would have considered the neighbors of E, and that's where those were those two, and then there were no neighbors of C. Oh, I missed one here. So by looking at the neighbors of B, which were these edges, and then the neighbors of D, and then the neighbors of G, and then of F, and then of E, and then of C, as you can see now, I put a line through every vertex, or every edge. As we look at the vertices one by one, edges one by one, as we look at the vertices through one by one, every edge is ultimately going to be departing from one of those vertices, and so we'll get that edge at that step. And what that means is, as I pass the loop one by one and look at the vertices one by one, and therefore the neighbors of the vertices one by one, what I'm getting over the course of the algorithm is every single edge. And so the overall time here is order E. It takes constant time to consider a particular target of a particular edge. And since at every pass through the loop, I'm considering all the neighbors of one vertex, and that means all the edges departing that vertex. Since over the life of the algorithm, I consider every vertex one by one, I will be considering every departing edge of every vertex one by one. And every edge is departing something, and so we'll be considering all the edges one by one. And so overall, we'll do this for every single edge. Now, sometimes there'll be an update caused, sometimes there won't. But at the very least, we will at least say for every edge, We're saying here's my target, my source, and now here's my target, and consider the edge from that source to that target and ask if that edge should cause an update or not. That process will take constant time, whether the update is caused or not. We at least have to do the comparison. And so as a result, we can say, well, every departing edge will force us to consider an update, and there'll be E edges, and we'll have to look at each of them once. And so overall, that'll take order E time. And so the table method here is going to be order V squared plus E, which is basically the equivalent of V squared because we know the number of edges at most can be V squared. You can have an edge from every vertex to every other vertex, and that's it. And so at most, we've got V squared edges. And so V squared plus E is either going to be V squared if the number of edges is really small, or V squared plus V squared if the number of edges is great. And so ultimately, that time can be V squared no matter what. So the question is, can we do better? And the answer is, well, it depends on what particular situation we have. Let's consider, again, what we're attempting to do here. We're attempting to traverse this table each time to find the minimum distance out of all the vertices that are marked unknown still, that still have 0 for k. And when we had them in a table, we had to search the table each time. Search all 7 vertices, confirm which one's the minimum, and then use that. Next step, search all remaining 6 vertices, confirm which one's the minimum, use that, and so on. Next step, search the 5 vertices, or actually search the whole table, but consider the 5 vertices that still have kv equals 0, and pick the minimum distance of those, and so on. What if instead we used a setup that was specifically designed to give us the minimum at each step? And there's a number of things we might do. What structure or what structures have we considered, have we looked at over the semester that would allow us to find a minimum element very quickly? And we might say, well, we can talk about the kinds of things we did before, where I say we've got here a AVL tree, and finding the minimum there is going to be log n time, and we have here a sorted list, for example. Finding the minimum there will be constant time. And we did look at a priority queue, or specifically the heap implementation of a priority queue, which we said is pretty much what we would use. And finding the minimum would be order 1 time. And then, of course, there was the idea of extracting that minimum. And so this was the ability to find it. We're also going to need to remove it. So to remove the minimum, I'll just write find a minimum here. To remove the minimum, this would take log n time, this would take constant time, and this would take log n time. And so the sorted list is looking really good, except we have to do the edge updates. And when you do an edge update, a vertex potentially changes in distance. We saw that here, for example. B got a smaller distance, D got a smaller distance. And so a sorted list bogs down there because essentially what you're doing is a reinsert. A vertex changes value, you now have to find a new place for it. And this then becomes the same discussion we went through when we talked about priority queues in the first place, where we said what we end up with now is, okay, if we're dealing with a sorted list, it's really easy to find and remove the minimum, but every time a vertex gets updated, we need to move that vertex elsewhere in the list to reflect its new position, because if a vertex gets updated, it now becomes the lowest current distance that needs to move to the front, for example. And so searching to find that new position would be linear time, where for the AVL tree and the heap, it would be logarithmic time to reinsert a updated vertex into a new spot in the structure. And we talked, of course, before about how the heap in general is going to be a little bit faster in constant factor than an AVL tree. And so let's use a priority queue to extract the minimum and take care of our edge updates, and consider how that would work. The idea here would be then, rather than traversing to find the minimum at each step, what we would have here with our heap, we'd have it set up something like this, where I'd have vertex A with priority 0. And then I'd have here, well, you know, I have F has priority infinity, and G has priority infinity, and I'd have here D and B and A, C and E. And so we'd start out with sort of every node having priority infinity except for A, which has priority 0. And we say the issue here, finding and removing the min each pass through the loop is going to be order log v time, because that was the cost of deletement on a heap. The issue would be, well, finding the A is easy, but now instead of keeping track of a known field and saying, well, every spot in the table, you know, we're going to say whether this vertex has been processed or not. We'll simply say, well, the ones that would hold 0 for your known field would now be the ones that are still in the heap. And as we delete them from the heap one by one, well, that's because we're choosing, okay, here's our minimum distance vertex. We'll now explore from there. Meaning we remove it from the heap and it's no longer in the heap. Here's our minimum vertex. We explore from there. And so we don't really need this field anymore, because now we'll simply say, well, if it's in the heap, then it's still being considered. And once it's removed for exploration from that vertex, it won't be in the heap anymore. The only point of this known field was to make sure we didn't keep picking A over and over and over again. We always said we're picking a vertex out of the ones that haven't been explored. When they were all listed in the table, we had to mark which ones we should still take seriously and which ones have been used already. And if we're going to store them in a data structure rather than having every vertex in the table, then that's a little easier to deal with. We can simply say, well, the ones that are still there are the ones we take seriously, and the ones that aren't there are the ones we don't. And so when I delete A, we would have done something like this, where I would have said, well, we now move E to the top. And then the issue is, well, I don't need to really bubble E downward, because E has the same distance as the others, which are infinity. And so in this case, the deletement is very straightforward, but that's just because it's the beginning of the algorithm and everything's infinity. But in general, you'd have to then percolate E downward to find it adjust to its new spot in the heap. And so finding and removing the minimum in each pass is going to be order V, or order log V, because that's the cost of delete min on A. Because we said delete min on a heap is going to be, in general, logarithmic on the size of the heap. And then so as a total cost, that's going to be V log V. If every delete min takes log V time, then total, you have to do V of them. You have to delete every vertex from the heap one by one. And so total, you have V log V time. And of course, then the issue we have with that is then as a result, or I should say, we also have to set the heap up, and that could be done using the build heap algorithm Adam discussed, or you could just have done, you know, insertions one by one into the heap. The point is that would be order V or order V log V itself, so it doesn't really make this worse. You know, you have V log V removal time overall, and then the setup time to begin with would have been equal or less than that. Now, here when we talk about the update of each edge, or update, update due to a new edge that we're looking at for the first time. Before it was constant time, now it's going to be a little different, because we might still have the ability to go from vertex to spot in the heap and vice versa. We need that to be in constant time for this to be accurate. So I can perhaps go from this spot in the heap to my vertex D and back to this spot in the heap. But now, it's not enough just to say, well, given the vertex A and the vertex B, and I know the edge between them, that's what we had before, I'll still have the graph set up itself. And so I can still say, well, given A, and then now I have the edge from A to B, and the vertex B, and let's consider all those. And let's do an update. So I update infinity to 3. Well, the issue is I'm not just updating that slot in the table. If I update this to 3, I need to now say, well, wait a minute now. The vertex B has had its key decreased and it needs to be percolated up in the heap to the proper spot. And so in general here, this is now not just some table entry. When I determined I wanted to do an update in the table implementation, I simply said, well, just go to the table and overwrite the distance field with a new distance. I'm not doing that here. Now I'm saying, go to the heap and update the heap entry with a new distance, which is fine. That's constant time. But now that can't stay there. If b goes from infinity to 3, b needs to percolate up. And that's what we didn't have with the table implementation. Going to the table and reading a field and updating it is one thing. Going to the heap and just updating it and leaving it there is something else. I can update that key from infinity to 3, just like I could update the table entry from infinity to 3 in constant time. But the table, then we were done. Where with the heap, b needs to be percolated up. And so every time that this happens, that's going to be log v, because there's v vertices in the heap. And so the increased key or decreased key involves percolating up or down, and that's log v time. And so your total here is going to be order E log V. Before we said the edge update is simply a matter of writing an update into a table or doing a comparison and writing an update into the table, and that was constant time. There were E of those, so overall you had total E. Now you're saying your cost is a matter of the constant time comparison, the constant time update, just as before, but now since it's not a table but rather a heap, you need to now say, well, now that this vertex has been updated, its spot in the heap needs to be changed. Unlike in the table where I just left b exactly where it was, once I updated b's distance, that was it. Now b needs to, it's the equivalent of moving b somewhere else in the table because of its update. And so that doesn't take constant time, that takes log v time for one of those updates. And each edge could potentially cause an update, and therefore every edge can potentially cause a log v decreased key operation, and so the total processing there is going to be E log v. And so therefore our total here, the overall is going to be order v log v plus E log v, or what that time is then is, let me scoot up just a bit, order quantity v plus E times log v. And how do that compare? Well, let's write that out here. We have the table method. And the table method is order v squared plus E, which was basically order v squared. And the heap method is order v plus E quantity times log v. So we have two different possibilities here. And one thing you might note here is, let's consider first the sparse graph, where, in other words, the number of edges is much less than v squared. In that case, the table method is worse, because if the number of edges is much less than v squared, then we say here, well, this quantity here will not be anywhere near v squared. What we basically have here is, well, v plus E will be, the number of edges is not going to be quite v squared, so this is more sort of a linear term, times log v. And so this quantity, if E is much less than v squared, we're dealing here with, up here we have, the table gives us v times v, and the heap method gives us certainly v plus E, but times log v. And the fact that this is so much less than that is going to offset the fact that now we have the edges added in here as well. Given in mind, too, also, this is going to be really plus E anyway. But that's not really going to factor into it too much. The issue is more here that here we're saying we have the number of vertices times the number of vertices. Here, we have the number of vertices times log v. And so what we're basically saying here is, if you kind of write these out longhand, this is v times v plus e. This is v times log v plus e times log v. And what we're saying here is, when e is much less than v squared, the v times log v compared to the v times v is small enough that the fact that we're multiplying e times log v instead of e times 1 is not going to be a big deal. This will turn out to be less. So for a sparse graph, we want the heap implementation, because this term, the difference between the v times v and the v times log v will be significant enough that the fact that we're multiplying e times log v instead of e times 1 won't quite make up for that, and so the heap implementation is better. For a dense graph, where e is approximately equal to v squared, or some pretty large constant of time, fraction of v squared, well, then the table, as we've talked about here, we have basically v squared plus v squared is order v squared. The heap implementation will effectively be v plus v squared times log v, which will be the equivalent of order v squared log v. Or in other words, for a dense graph, the table implementation is better. The heap is actually worse than the table, and you ask, well, how can that be? The minimum is so much more efficient. With this table, we're doing this order v search for the minimum, and for the heap, we get the minimum in log v time. And the answer is, we'll come back to this calculation here. Now we're saying we're doing a log v search rather than a v search, but each update takes log v time rather than constant time. And there's our trade-off here. When we move from the table to the heap implementation, we're saying our vertex detection, our picking of the minimum is faster, but each edge update is slower. And that's okay for a sparse graph, because we don't have enough edges for that to matter. For a dense graph, we have so many edges that making the edge updates, the comparisons and such, making those take longer because of the percolation up for the decreased key. Making that take more time now results in so much extra time, because each edge has that time added to it, or there's that time added to it for each edge, and there's so many edges that now the number of vertices and the fact that we're saving our search time doesn't quite make up for it. We're saying for the dense graph, the e times log v versus the e is so much greater that the difference of v times v versus v times log v isn't going to quite make up for it. They say, yeah, fine, it doesn't take quite so long to search the set of vertices each time. But the edge updates are so expensive that it doesn't matter. The edge updates being more expensive results in a greater time than is made up for by the increased, or the improved vertex search time. Or for a sparse graph, the improved vertex search time is enough to make the heap selection better, because we don't have many edges, and therefore this doesn't come into play. As the edges increase, the difference between e times 1 and e times log v increases, and eventually gets so great that it overtakes whatever advantage we got from an improved vertex search. And so that's the difference. As we add edges to the graph, eventually this e times log v term gets larger and larger and larger in comparison to the e times 1 term, that it eventually overtakes any improvement we got by going from v times v to v times log v. So for a sparse graph, the heap implementation is better. For a dense graph, the table implementation is better. And we could, of course, have said, for an adjacency matrix implementation, well, we have there, by necessity, we have to look at every single possible vertex whenever we do the neighbor search. So we may as well just use the table implementation, and it's as if we had every possible edge, because for every vertex, we'll have to look at every neighbor, or we'll have to look at every other vertex. There won't be the possibility of saying, well, for vertex A, I only look at B and D. We'll have to look at every single, B, D, F, G, C, and E, and say, well, 4 of these are not even my neighbors, so forget about them. But 2 of them are, and we proceed from there, processing there. And so the heap implementation wouldn't really give us anything, any advantage there, because I'd have to look over all the vertices, just the fact that when I look over my neighbor list, I can only do that by looking over all the vertices. And so the adjacency matrix will be order v squared anyway, to search over the neighbors of each vertex each time overall. And so we may as well just use the table implementation. So if you have an adjacency list, you can improve the running time if you have a sparse graph. If you have a dense graph, you're stuck with v squared. If you have an adjacency matrix, simply traversing over each vertex, one by one overall, will take v squared time anyway. And so you're not going to get any improvement if it's a sparse adjacency matrix. So you just go ahead and use the table implementation, and you know that it will be at most v squared, and then v squared traversal time added to that is v squared. And so that's a discussion of the implementation of Dijkstra's. You have 2 different implementations, and one of them is good for some graphs and some implementations of graphs, and some of them are good for other implementations of graphs. Now, when we talk about prims, and let's go ahead and put up the graph we dealt with when we dealt with prims. Actually, here it is. What we face with Prim's algorithm is something very similar to Dijkstra's, even though it might not look like that at first. Remember, what we had done here was we said, well, A is our source vertex, so let's consider all possibilities from A, and that were, these edges here. And I said, well, which one do I want to add? And I said, well, what I want to add is the A to D edge, which is of weight 2. And so it said, okay, well, now that's added to my tree, and ignore this for the moment. But I said that's added to my tree, and now from D, I can consider then, once this is added, and I'll just sort of darken that in. Once that's added to my tree, now I consider not just stuff from A, but stuff from D as well. Because now A and D would both be in set S. By adding the A to D edge, we would have moved D from the set N to the set S. And now we were asking at this sort of second step, now consider all the edges that go from A or D to the other vertices. Now which one's the lowest out of those? And that was how we proceeded with prims. And in the last lecture, I always had a slash through the edges we were considering at this step. Well, now consider this closely here. Well, I have 2 possible edges to B. And the problem here comes, and we look at this and we say, well, I've always got to keep track of all these edges at each step and find out which edges can be considered and which edges can't, because, of course, once I add the B to D edge, as we did last time, now the A to B edge would cause a cycle. It's between 2 vertices in set S, and it couldn't be considered any longer. And we went through that last time. But the complication here comes with trying to look at all the vertices, or I'm sorry, all the edges at once. Okay, we've got all 5 of these that we're considering, all 5 of these marked edges. And in reality, there's really no need to consider the A to B edge. The reason being, our goal here is to connect B to our minimum spanning tree with the lowest possible choice. And this is part of why the algorithm works in the first place, though, like I said, we're not going to formally mathematically prove anything. But the issue would be, if we had connected in our original minimum spanning tree, if I had connected B to A through this edge of weight 3, I could always have said, well, wait a minute, if I ditch that edge and add the B to D edge instead, that will still connect B to the tree. Anything that was connected to B will therefore still be connected to the tree. So the issue is one of saying, well, do I want to say I've got stuff connected to B like that, or do I want to say I've got stuff connected to B like that? Either way, everything that we may have added to the tree by connecting it to B is still connected to the tree. It goes BAD or BDA, but anyway, all these things that might be connected to B are part of the tree either way. The only question is, am I connecting B to the tree through an edge of weight 3 or an edge of weight 1? And clearly that's the better choice. However we've got things arranged here, if I had this situation in my tree, I could just replace that edge with that one, and I would improve my tree, which is part of why the greedy strategy worked. So whatever else is going on, if the rest of my tree I haven't really drawn, but however these things are hooked to B, if I had my full answer here and I replace that edge with that one, the A to B with the A to D, that improves my minimum spanning tree. And that's why we would have picked this edge to begin with. The point here being, I'm faced here with a choice of saying, I can connect B to this minimum spanning tree either through A or through D. Since the D edge is better, it's lower, why on earth would I ever pick this edge? It gains me nothing. If I want to attach B to the minimum spanning tree at any point, given the choice of those two edges, you'd always want to pick the B to D one. It's lower. And like we said, anything you were going to attach to B is still attached to B regardless of how B is attached to the graph. So anything that you may have hooked to B is then connected to the rest of the tree through that edge, or you've hooked it to B and it's connected to the rest of the tree through that edge. There's no difference there except the weight of this edge. There's no benefit gained by picking this edge over this one. So why even consider it anymore? What we've effectively done is, when it comes time to look at the things that the connections that can be made from D, we are now saying, well, formerly I may have connected B to A, but now I found a better way to connect B to my graph, namely through D. So forget about the A to B edge. It's useless now. If we're going to attach B to our minimum spanning tree, we would do it through the B to D edge unless we find a better edge later on. That is, what we're in effect saying is, every time we look at a new neighbor, we say, is that the case? Consider the distance to a current vertex, such as, let's say here, we said, after we started with A was our source vertex, and I said, well, whoops, dang. Everything I just said for the last 5 minutes. That should have been C, because that should have been C. If you want to make it the graph we had last time. I'm very sorry about that. I just noticed that now. So that's what I get for preparing slides in advance, or some of them. Anyway, so that should have been C, that should have been C, and that now matches the graph you had in the last lecture. I apologize. Same explanations, just different letter. So, that said, what we could have done here is said, well, when A was our source vertex, we looked at the various neighbors of A, and I said, well, I can reach vertex C in length 3, I can reach vertex B in length 13, and I can reach vertex D in length 2. And now I finished processing A. That means A is in the set S, or it always was, but now I've sort of finished that. That's been added to the tree. We know that's added to the tree for sure. And I went ahead and picked vertex D. That's much like Dijkstra's, where we're saying, look at all the vertices that are still not added to the tree, still have KV equals 0, and pick the lowest of those. That's essentially what we did with Prim's. We said, consider, out of the group of edges I'm considering, the ones that go from S to N, pick the lowest edge. And in this particular step, the three non-infinity vertices are the ones that go from S to N. Or I'm sorry, the three non-infinity vertices are ones connected with edges that go from S to N. These are as well, but we haven't even seen those. So when I pick the A to D edge, because it's the lowest of AC, AD, and AB, in effect this table gives us that same idea and says, well, those are the three distances of three vertices we actually can reach at this point. Pick the lowest of those, add that to the tree, and now explore from D. And I can say, well, from D now I have a neighbor E, so that can be updated to 9. I have an edge to G, so that can be updated to 11. I still haven't reached H, which should have been in the table. I haven't reached H or F yet, so those still have infinity recorded. And the issue of C here is one where I said, you know, earlier there was a possibility of connecting C to the graph through an edge of weight 3. I was saying B before, it's vertex C. I could have connected C to the graph through a vertex of, or through an edge of weight 3. Now I find a better way. I say, well, look, I've got an edge from D to C. I could connect if I'm going to connect the vertex of weight C, I could connect it to D instead of to A. Which means what I could have done is updated this to 1. That is, I can ask for, in prims, if the distance at my neighbor, the neighbors of D are what we're looking at here, for all my neighbors, if the distance there is greater than, man, I'm just making all sorts of mistakes on this piece of paper. If the distance recorded at that vertex is greater than the new distance from where I am to there, then update instead. That is, it's exactly Dijkstra's minus the previous path stuff. I don't care how long it took to get to D. What I care about is, well, now I've got an edge from D to C. However long it took to get to D, who cares? That's not what minimum spanning tree is concerned about. What we are concerned about is, let's connect C using the lowest possible way. And I had a way to connect C to A, so I had that edge weight stored. Now I've got a way to connect C to D, so I consider that new edge weight. I say, now that I've got a new way of connecting C to the graph, is it better or worse than the old way? And since it's better, I store the new way instead, and therefore, because I'm storing the new way, the old way now never gets considered. And effectively, even though it doesn't have to be, effectively we now, that's a black X through that vertex, or through that edge. In prims, we still said, well, that's a possibility. But in reality, okay, when we just kind of draw prims out on paper, we would say, well, we can pick either of those two edges. But in reality, because of the presence of this edge, we would never pick this one. So even though you still say, well, those are in set S, that's in set N, so you can pick either of those two edges, and so you consider them both abstractly, conceptually. In reality, we would never consider this once we've got that choice open to us. So when it comes time to implement prims, all we need to keep track of is that edge and not this one any longer. And the same thing goes then when it comes time to pick C and we say, okay, we'll now add this edge to the tree. That means then that we are considering all the edges that go from A, D, or C to the other vertices. And all that means here is we're saying, well, I could connect now on the next step, I'll be able to consider the D to G or the C to G edge. And in this implementation, we'd say, well, I had an edge of weight 11 before that could have connected G to the graph. Now I've got a new edge, C to G, which is of weight 15. And we say, well, forget about it. In this case, the new edge we found for connecting G to the graph is worse than the old edge that we could have connected G to the graph with. And so we don't do an update. And so even though prims would have been saying conceptually, these are the two of the edges we can consider at the next step, in reality, we'll never consider this one. Because if we're going to connect G to the graph, right now, that's a better way to do it. So at step 1, we say, well, these are, A is our source. We know that. And we process from A and consider we have now 3 edges, to C, to D, and to B. And we pick the lowest of those. And at each step, then, we consider exactly one edge to some of the other vertices. When I've added D to the tree, now I'm saying I consider this edge connecting C to the tree, this edge connecting B to the tree, this edge connecting E to the tree, and this edge connecting G to the tree. And I add this D to C edge. So now I say, well, I could have considered this edge connecting G to the tree, but that one's better. And so I consider this edge connecting G, that edge connecting E, and that edge connecting B. And out of those, this is the best one, so I go ahead and add this, which would, in theory, add those 4 edges to consideration. But now we say, well, out of 11 and 7, 7 is the better choice. And so I'd say I'm actually better off saying, well, there's no need to consider both of the edges to G. Forget about this one. And now this will be the edge to G that we keep track of. Likewise, we have only one edge to H, only one edge to F, and we say I have two edges to B, I don't need to consider them both. The E to B edge is much better than the A to B edge, so I update that to 1 and forget about this one. We only need to keep track of the current edge to B, the current best edge to B, the current best edge to F, the current best edge to H, the current best edge to G, and that's what I've done here. E to G is the current best edge to G, E to H is the current best edge to H, E to F is the current best edge to F, and E to B is the current best edge to B. And that's why I'm not worrying about this edge or this one or this one. Even though conceptually, when we talked about prims last time, those were among the edges we were quote-unquote considering. But in reality, we'd never pick them because we have better alternatives. And so when it comes time to implement prims, we only need to keep track of the best alternative so far. And eventually we'll reach the point right before we add the H to G edge where we'd say, well, we could have considered all 4 of these edges. But really, we only need to keep track of this one because that would have been the best choice of G we'd found so far. So if we're going to add G to the graph, we wouldn't have added it through this edge or this one or this one. We would have added it through this one. And so once we find that edge, that's the only one we need to keep track of. And so that would be how prims would work. It's just like Dijkstra's, but we've removed the dv part. Instead of saying is, because here's Dijkstra's, we'd be asking, is that's the comparison we had for Dijkstra's, and we're just saying, forget about the previous path part. We're simply looking at the immediate edge and nothing else. And so that's all there is to it. Of course, we can always keep track of the vertex that we attached a vertex to the tree with. We could have done that for Dijkstra's as well. I'm just showing the basic idea of how we'd kind of process through this. And so that's the idea behind implementing prims. We don't need to keep track of all these edges at each step. Just keep track of the best edge that attaches each vertex. And as you find a better edge to attach vertex, for example, finding a better edge to attach G, then get rid of the previous edge and keep the better one. And so that only requires us then to keep track of, a certain number of edges at each time, and that makes it much easier to deal with. And that's it for prims. And so the running times then become the same as we talked about for Dijkstra's. Kruskal's is the easiest of these to talk about. We have here the idea of, if we kind of put this graph back, here's E and here's F. Kruskal's, remember, was the algorithm where we said look at all the edges one by one, and we consider them if they we consider the edges one by one in order from low weight to high weight, and if they cause a cycle, we reject it, and if it doesn't cause a cycle, we accept it, and we keep doing that until we accept 7 edges, and then we're done. Or accept v minus 1 edges, and then we're done. And so in this case, we had actually gone and listed all the vertices in order in our example in the last lecture, where I actually made a list down this column, and I said, well, we've got the B to E edge, which is of weight 1, and we've got the C to D edge, which is of weight 1, and the A to D edge, which is of weight 2, and we had then the A to C edge, which is of weight 3, and so on. And the easiest way to keep track of those would be a heap. Or I can insert the edges into the heap, and at worst, order E log E time. Because I'm putting a bunch of all the edges into the heap one by one. Each insertion is log E in the worst case, and there's E total insertions, and so E log E total time. And then as I remove the edges one by one, that likewise will be order E log E time. I say, okay, all the edges in our heap, now I consider them in order from low to high. And so I say, well, the lowest weight edge I get by calling delete min on my heap. The next lowest weight edge I get by calling delete min on my heap. The next lowest weight edge I get by calling delete min on my heap. The next lowest weight edge I get by calling delete min on my heap, and so on and so forth. And so that's all there is to that. Question is, how do we determine cycle connection? Because that was the tricky part. We said, okay, I just want to kind of go down the list of edges in order from low weight to high weight and at every edge say, does this cause a cycle or not? And if it doesn't cause a cycle, I'll add it to the tree, and if it does cause a cycle, I won't. And so this part's the easy part, saying, well, let's just arrange we could have sorted the edges too, and this essentially is kind of the idea of heap sort that I'd mentioned, where we're saying, I can sort them all by just dumping them all into a heap and then pulling them out of the heap one by one. It's an easy arrangement of the edges. We could have also put the edges in an array and sorted the edges and then looked down the array cell by cell. So that's fine as well. Ultimately, it's going to take E log E time to even sort the edges using even the best sorting algorithms. And so it's essentially the same idea, where we'd say I can sort these edges in order and then look at them one by one. The tricky part is saying, given an edge, I want to determine whether a cycle is caused. And so we start out saying, these are our edges, these are our vertices. And the first edge we add is the B to E edge, and we say, does that cause a cycle? No, so we'll go ahead and add it. And then we say, well, this is next possible edge, does that cause a cycle? No. And this is the next possible edge, and that doesn't cause a cycle, so we'll add it. But then this edge of weight 3, which would be the fourth edge we consider, that does cause a cycle, so we would not have added that. And the question is, how can we know? How can we know that A and D and C are connected already, and so we should not add the edge A to C? And if you'll notice here, connection is an equivalence relation. Because, of course, every vertex is connected to itself, and if C and D are connected, then D and C are connected. Connection works both ways. And also, if C and D are connected and D and A are connected, then C and A are connected. There's a path. If there's a path from C to D and from D to A, then there's a path from C to A. Which means we can use disjoint sets to model this. I could have had each of the 8 vertices in their own set, and what I've done then is, by adding this edge, I've done a union of those two sets. And by adding this edge, I've done a union of those two sets. And by adding the A to D edge, I've unioned the set CD and the set A. And so now with all 3 of those in one set, trying to add the edge from A to C won't work because we say, well, wait a minute, we know A and C are already connected because they're both in the same set. When I added C to D, I unioned sets C and D. When I added the edge from A to D, I unioned the C to D set, or the C and D set, and the A set, and had now a set CDA. And so now that those are all in one set, doing a find on both of those would give me the same set, and so I shouldn't add that. So our procedure here will be when considering an edge, we'll say here, do we find on endpoint 1, do we find on endpoint 2 if the results are the same, then a cycle would be caused. Because if I do a find on endpoint 1 and on endpoint 2 and get the same result, it means endpoint 1 and 2 are in the same set, which means they're connected already, and so connecting them a second way would cause a cycle. On the other hand, if the results are not the same, it means the 2 endpoints are in different sets. Now, for example, if I go to insert the edge from G to H, which was a weight 4, well, G and H are in different sets. It's okay to add that edge. Adding that edge would mean doing a union on those 2 sets. So otherwise, do a union on endpoint 1 and endpoint 2. And that's how we'll do our cycle connection. We can go ahead and deal with the arrangement of the vertices simply by putting them in a sorted order or dumping them into a heap and reading them from, deleting them from the heap one by one. As far as the edge considerations go, you simply say, well, every time we want to consider an edge, do a find on the 2 endpoints, and if the 2 vertices are not in the same set, then you would, of course, add that edge to the tree, and you'd union the 2 endpoints. And you'll ultimately do 7 unions before all 8 vertices are connected. Because now we'd say, well, the edge of weight 5 would be next, and the edge of weight 6 would be next. But then we would reject that edge because B and F are in the same set. And we'd reject that edge because G and E are in the same set. And we'd reject that edge because H and F are in the same set. And then finally we have this set, and we add the D to E edge of weight 9. And that's exactly how we proceeded in last lecture's example. We rejected this edge, and when it came time, we rejected that edge, and that edge, and that edge. The B to F, the G to E, and the H to F edges, because each of them would cause a cycle. And we knew that because at this point, B to F were in the same set, G to E were in the same set, H to F were in the same set, but D and E were in different sets, so adding the edge between them was okay. And that would have been our 7th union, and then we would have been done. So what this means is for every edge, we will do 2 find operations. And overall, we'll do V minus 1 unions. And so if we have V minus 1 unions plus 2 times E finds, remember our rule that said it's order m log star n, where m is the number of operations and n was the number of elements. Well, the number of elements here is the number of vertices. So the total running time for this would be order V minus 1 plus 2E times log star of V. That's going to be the cycle detection cost. Our disjoint set result had been that for all disjoint sets, if you do a bunch of unions and finds, the total cost is m times log star n, where m is the number of operations and n is the number of elements. We have V elements, we have that many unions and finds. 2 finds for every edge, V minus 1 unions total, and so the total cycle detection time will be V minus 1 plus 2E quantity times log star V. However, keeping in mind that this was our edge selection cost, keeping in mind how small log star V would be, this term is much larger than this. The log star V, remember, was very, very, very small. Effectively, this is almost constant time. Or I'm sorry, effectively, the log star V is almost constant time. This is almost V minus 1 plus 2E, because this log star V is so small. And so comparing V minus 1 plus 2E compared to this, E times log of E is going to be much greater than this. Is just going to be almost, on the level of V plus E. A few constants are different and such, but this will be on the order of V plus E. And this is E times log E, which will be a much larger term. So the cycle detection is really so fast that it doesn't really matter too much at all. The dominant term is the edge selection, and so that's E log E time. And that's what will dominate Kruskal's in terms of a running time. Now we may remember that you can sort of do, we said our insert would be E log E, but you can just dump everything into an array, insert edges into the array, and order E time, and then use the build heap algorithm that Adam had discussed, so that you can say, well then in linear time I can arrange them in a heap, and then we can remove them in each time and order E log E time. We could have sped things up slightly by doing that. That's saying I don't need to insert all the edges one by one into a heap. I could have just dumped them into an array in linear time, then a build heap in linear time, and then the removal cost would be E log E. And the benefits to that is if I stop early, and for example, we stop at this point, I don't ever need to consider the C to G edge or the A to B edge, for example. If we manage to stop early, then we don't have to do a removement on every single edge. In that case, we can sort of think of our running time total as order F log F. where f is some value less than e. F is the number of edges we actually look at, all the edges we actually add to the tree plus the ones we rejected before that. And then at that point we could end our structure, end the algorithm. We don't need to go through and explicitly reject all the remaining edges, and we don't need to chew up that time. So sometimes, and even the book refers to the running time as f log f, it's e log e, but we don't actually have to look at every single edge, because once we've added all the edges we need, the rest of them would just be sitting in the heap. We don't need to delete them from the heap and reject them one by one. We can just say, okay, algorithm's done, and then call destructors and wipe out all the structures that we've built. So, and the reason we can then consider that is because the insertion time doesn't take e log e. It's linear if we do the right algorithms, and so that means the deletion of the minimum comes to dominate the running time. And so if it's a little less, if we stop early instead of going on to delete min the edges we know we're now going to reject, all the rest of them, then if we stop early instead and say, well, I just added my last edge, I'm done, then that saves us a bit of time. So that's the Kruskal's running time. Either of these would be acceptable as, a running time for Kruskal's. The point is that the cycle detection is very short, very quick, and so the edge selection, selecting the minimum edge each time, is what dominates the running time of Kruskal's. And that's why if we once we've selected all the edges, if we stop and don't keep removing the minimum edge just to reject it, and now remove the next minimum edge just to reject it, if we stop early, if we stop once we've got all the edges we want, then that will speed things up just a bit. And so that's the implementation of Kruskal's, and with that, we're done talking about the graph implementations. Next time, we're going to discuss breadth-first and depth-first search, the two traversal methods in graphs, and we will then proceed from there by with topological sort. And I will then see you next time. Take care.